Have you ever wondered what's happening inside your phone or computer right now? It feels like magic, doesn't it? Billions of calculations per second, letting you watch this video, chat with friends, and browse the internet all at once. But what if I told you it all boils down to something incredibly simple? A tiny switch, a microscopic gatekeeper of electricity called the transistor. And the story of how we took this simple switch and turned it into what we now call artificial intelligence is one of the most incredible journeys in human history. So, how do we get from a simple on-off switch to something that can recognize your face, compose music, or even beat the world's best chess players? Let's break it down. First, let's really understand the transistor. Imagine a light switch on your wall. It has two states, on and off. A transistor is essentially that, but mind-bogglingly small and fast. Instead of your finger flipping the switch, a tiny electrical signal does the job. A little pulse of electricity comes in, and the transistor either lets a bigger current pass through that's on, or it blocks it that's off, on and off. 1 and 0. This is the fundamental language of all computers, binary. Okay, so we have a bunch of tiny switches. How is that useful? Well, what happens when you put two switches together? Let's say you connect two light switches in a row to a single light bulb. The bulb will only turn on if BOTH switch 1 and switch 2 are on. Congratulations, you've just built your first logic gate. This is called an AND gate. If A and B are on, the result is on. Now, what if you wire them up differently, in parallel, so the electricity can flow through either switch 1 or switch 2 to get to the bulb? Now, the bulb turns on if either switch is on. That's an OR gate. And finally, you can build a NOT gate. This one is a bit like a rebellious teenager. If you give it an on signal, it outputs off. If you give it off, it outputs on. It just inverts whatever you give it. With just these three basic building blocks and OR and NOT, you can construct any logical operation imaginable. It's like having only 3 Lego bricks, a red one, a blue one, and a yellow one, but with an infinite supply. You can build anything from a simple house to the entire Death Star. These logic gates are the words and sentences that allow transistors to think. By combining millions of these gates in incredibly clever ways, engineers built circuits that could perform arithmetic. They created adders, which can add two binary numbers together. Then they built circuits to subtract, multiply, and divide. This collection of arithmetic and logic circuits forms the heart of a computer, the central processing unit, or CPU. The CPU is the workhorse. It follows a list of instructions, a program to the letter. Fetch an instruction, decode it, execute it, add this number, move that piece of data, compare these two values. It's incredibly fast and efficient, but it's not exactly intelligent. It's just a hyper-obedient, lightning-fast calculator. For decades, this was the paradigm of computing. We, the human programmers, had to painstakingly write out every single step. If you wanted a computer to identify a cat in a photo, you'd have to write code like, look for pointy ears. Now look for whiskers. Now check for a specific fur texture. It was brittle, ridiculously complex, and would fail if the cat was turned at a weird angle or in bad lighting. There had to be a better way. The breakthrough came from looking not at electronics, but at biology, specifically the human brain. Your brain isn't made of logic gates. It's made of billions of neurons. Each neuron is a simple cell. It receives signals from other neurons, and if those signals are strong enough, it fires off its own signal to others. Sound a little familiar? A neuron receives inputs, and based on some threshold, it produces an output. It's not exactly a transistor, but there's a fascinating parallel. This insight gave birth to the idea of an artificial neural network. Instead of hard-coding the rules, what if we could build a system that learns the rules on its own, just like a brain? Here's how it works. We create a network of artificial neurons, which are basically little mathematical functions, all connected to each other. We organize them into layers. You have an input layer where you feed in the data, say, the pixels of an image. You have an output layer which gives you the answer like cat or dog. And in between, you can have one or more hidden layers where the real magic happens. Each connection between these artificial neurons has a weight. You can think of this weight as the strength or importance of that connection. A high weight means the signal passing through has a big impact. A low weight means it's less important. When we start, all these weights are set to random values. The network is a blank slate. It knows nothing. So, if you show it a picture of a cat, its output will be complete gibberish. It might say car or banana with equal confidence. But here's the crucial part. We know the correct answer is cat. So we can calculate the error, the difference between the network's garbage output and the correct output. We then use a clever mathematical process called backpropagation to go backward through the network and slightly adjust every single one of those connection weights. The goal is to make the error just a little bit smaller. We repeat this process over and over and over again. We show it another picture of a cat. It gets it wrong. We adjust the weights. We show it a picture of a dog. Tell it no, that's a dog, and adjust the weights again. We do this millions of times with a massive data set of labeled images. Slowly, almost magically, the network starts to learn. The weights are no longer random. They start to form a structure that represents the features of the things it's learning. The first hidden layer might learn to recognize simple things like edges, corners, and color gradients. The next layer might combine those edges and corners to recognize more complex shapes like eyes, ears, and noses. The layer after that might combine the eyes and noses to recognize faces. And finally, the output layer takes all this information and makes a final decision based on the presence of these combined features. It's highly probable that this image contains a cat. The intelligence isn't in any single transistor. It's an emergent property of the entire system. It's in the specific values of those millions of weights, finely tuned through an immense process of trial and error. The transistors aren't making a conscious choice. They are simply the physical medium that allows these mathematical operations to happen at an incredible speed. The intelligence is in the architecture of the network and the data it was trained on. This is the foundation of modern AI, or what we call machine learning and deep learning. When you ask a smart assistant for the weather, it's a neural network trained on vast amounts of human speech that converts the sound waves of your voice into text. When a streaming service recommends a movie you might like, it's a network that has learned patterns from the viewing habits of millions of users. So we've gone from a simple on-off switch to complex logic gates. From logic gates, we built CPUs that could execute instructions. And from there, inspired by the brain, we used these computing resources to simulate neural networks. We leveraged the raw power of billions of transistors, not to follow explicit rules, but to learn their own rules from massive amounts of data. The transistor itself isn't intelligent, but by arranging billions of them into the right structure that mimics, in a very simplified way, the learning process of the brain, we have created something that can perform tasks that we once thought required human intelligence. It's not magic. It's the beautiful result of decades of innovation, combining electrical engineering, computer science, and even a little bit of neuroscience. It's the story of how a simple switch, multiplied by billions and organized with genius, learned to see, hear, and understand our world. Thank you so much for watching. If you enjoyed this journey from sand to silicon to intelligence, be sure to hit that like button and subscribe for more deep dives into the technology that shapes our world. See you in the next one.